we're going to spend a lot of the time in this class solving systems of equations. So if you guys remember, linear algebra rules of array multiplication provide a convenient way for writing a system of linear equations. Linear meaning our highest power is x to the 1. Okay, keep that in mind, x to the 1. And we have ax equals b. We've already seen that the solution is A inverse times B. In MATLAB, it's A left divide B, and you'll be doing that quite a bit. But now let's talk about what it means to actually find the inverse and use different ways in order to solve these systems. Okay, so if we look at a system of equations, you can see here in this table, this is our generic form of writing a system of equations. We have AX plus by plus cz equals some constant. And we can write it as ax equals b, where a is our matrix of coefficients, x is our vector of unknowns, and b over here is a vector of constants. And we already know the solution. So each row in A can be viewed as a dot product of row I with the x vector. So if you remember, a dot product is a element 1 times this, plus this, times this, plus this, times this, plus this, times this, which is just this equation here. It's just that equation. Okay, so each row can be viewed as a dot product with our x vector. And it turns out our rows can also be thought of graphically as a line. And you've done this before when you've looked at solving systems of equations by looking at the intersection, where each equation is a line on a graph. And although now we have more than 2 dimensions. Each column, though, can be viewed graphically as a vector, which means our system of equations can be viewed as a linear combination, which we talked about in week A material. So let's look over here. So here I have different ways we can write our system of equations. So let's say we have the system 4x plus y minus 2z equals 0, etc. So I can write it as a linear combination. I can write it where each column of A is a specific vector. So if I look at these elements in front of x, that's my first vector. Then I've got these elements, I'll make it blue, in front of y. Note there's a 0 in the middle in my second equation, which I guess I can move that over, make it much more explicit. So these numbers here are my second vector times y, and these numbers here are my third vector times z. So I can think about it this way. This is my linear combination. A scalar times a vector plus a scalar times a vector plus a scalar times a vector equals my b vector. Okay? Or if I write it as ax equals b, it's like this. It's like this, where here's a, here's x, here's b. And it turns out our solution for a linear system is just a set of numbers that satisfies our equation. It doesn't really matter what letters we use for our unknowns. It just matters what our constants are, our coefficients are in A, and our constants are in B. So we don't even really need to keep track of these unknowns. We don't care what they're called. It's just our first unknown, second unknown, third unknown, fourth unknown. As long as A and B are set up correctly, then we don't care what those are called. So we have another way to write a system of equations, and this is right here, an augmented matrix. And we will see the augmented matrix extensively in this week's material and beyond. Okay, so here's our augmented matrix, where we've got our A vector here, or our A matrix on this side, and wrong letter, A, and here's B, where we just have a line in between here that just says, hey, this line delineates where A ends and where B begins. Okay, so we just collapse these two into one matrix. Okay, so here are the 4 different ways we can more or less write our systems of equations. They're all the same system, doesn't matter. We're just identifying it in different notation. So you are used to number 1. Last week we introduced number 2. And you're used to number 3. We introduced that a while ago, but now we've got number 4. Okay. So keep that in mind. Okay, so this week material is all about elimination. It's all about elimination. And if you think about solving your systems of equations, if you have 3x plus 2y equals 7 and negative 3x plus y equals negative 2, no idea if this gives me good numbers, but you know how to solve this a couple different ways, but one of those ways is elimination, where you can go ahead and add your equations together to remove unknowns and solve for another unknown. This is what we are going to be doing this week. But in order to do those steps, we need to understand how we can manipulate these equations before we add them together. So elementary row operations, these are the set of rules that we can use in order to manipulate a system of equations to make it easier to solve. So my first row operation, RO1, we can multiply an equation by a constant. So if I multiply this equation by negative 2, I get 6x minus 2y equals 4. It's the same equation. It's just scaled. It just has bigger vector values here. But essentially just taking this line and making it longer, which it already goes to infinity. Okay? But it's the same equation. So we can multiply a row or an equation by a non-zero constant. If you multiply as a 0, obviously that doesn't do anything meaningful. Row operation 2, we can rearrange them. So it doesn't matter if I write it as 3x plus 2y equals 7 or negative 3x plus y equals negative 2 versus 3x plus 2y equals 7. It doesn't matter which order I write my equations in. It's still the same system. As long as they're the same equations, it doesn't matter the order. Okay? And then row operation 3 is where we can do that elimination step, where we can go ahead and we can say add equation 1 to equation 2. These ones cancel. This gets me 3y equals 5, and I can solve for y. Once I solve for y, then I can go ahead and plug it into one of the other equations and solve for x. Okay, but this is my elimination step, where I add equations together. So those are the 3 rules we can use. And what we're going to do is we're going to apply these 3 rules in a systematic manner in order to solve our system equations by ignoring our letters here, ignoring these letters, and solving our system using our augmented matrix. So let's look at how we can do this. The first method we are going to use is Gauss elimination with back substitution. So what we're going to do is we're going to take an augmented matrix, and we are going to apply those 3 rules over and over and over again until we get to something called row echelon form, REF. And it's defined by the following characteristics. The pivots. So if I look at a matrix, we're trying to get it into something where we have a lower triangle of zeros. We're going to get a bunch of zeros down here at the bottom because that's what we did when we eliminated, right? We tried to get one of our unknowns to be 0. That's what it's going to look like in our augmented matrix. We're going to try and get a bunch of zeros. The element that is not 0, the first element in a row that's not 0, so 7, 2, 1, 9, 4, etc. The first element that's not 0 is called a pivot. So this is a pivot, and this is a pivot, and this row doesn't have any pivots because it's all zeros. So in row echelon form, the pivots are the first non-zero entries in the rows, and each pivot is going to be, below each pivot is a column of zeros. So below this 2 is all zeros, below this 7 is all zeros. Okay. Row echelon form is defined by the pivots being in a staircase pattern, where each new pivot, or each pivot in the row below it, is at least a column further to the right. So I've got this staircase pattern that shows up. Okay, and then you can have as many zeros as you get in the matrix, but if you have a row of all zeros, it comes down at the bottom. Okay, so we are trying to apply our 3 elementary row operations, our 3 rules, in order to get this matrix, get our augmented matrix into row echelon form, where we have this lower triangle of zeros that show up, where we have our pivots in a staircase pattern, so that we can solve our system. Okay, so for example, here we have an augmented matrix. I'm going to go ahead and try and make this a 0. I'm going to try and remove, so note this comes from 7x plus 0y minus 5z equals 3. I'm going to go ahead and try use one of these other equations that appears so that when I add it to 7 here, it disappears. So in order to do that, I don't need to do that. In order to do that, I'm going to go ahead and multiply row 1 by row 1 times 7. When I do that, I get 28, 7, negative 14, 0. And then the other equations stay the same. I didn't do anything to those. And then I'm also going to go ahead and multiply row 2 times 4. So row 2 becomes 28, 0, negative 20, and 12. And row 3 doesn't change. Now I can go ahead and do an elimination step. I can say row 2, I'm going to replace it by saying row 2 plus row 1, or minus row 1. So row 1 doesn't change. That equation stays the same. And row 2 now becomes 28 minus 28, which is 0. That's my elimination step. 7 minus 0 is 7. Negative 14 minus 20 is 7. And 0 minus 12 is negative 12. 4, negative 2. And there we go. I have gone and I've gotten a 0 in this location here, where 28 is my pivot above, so I want zeros all below it. And what we're going to do is we're going to keep going, keep doing elimination steps, keep using our row operations until we end up with something like this. Let me go ahead and write what REF might look like. But we want these zeros here, where I want these ones to be a 0 and change that row so I have zeros. Where this 28 is my pivot, put zeros below. This 7 is my pivot, put zeros below. That would be REF for this matrix. Okay, so our general approach to using Gauss elimination is to write our augmented matrix for the system, use our elementary row operations, go ahead and rearrange our rows if we want, multiply our rows by a constant, add our rows together to replace things until we get to REF. And then when we do that, we're going to have a new system, or we're going to have the same system equations, but now with all these elimination steps. So if I think about, let me erase some stuff. If I think about this equation here now, it's the same equation I had here, except I've modified it. So instead of it being 7x plus 0y minus 5z equals 3, it now becomes 0x plus 7y plus 7z equals negative 12. And if I get to REF, to row echelon form, I can rewrite my systems of equations, and you'll notice it's much easier to solve then. Okay, so the process of now solving our system equations, this last one when we get to REF should be 0x plus 0y plus something z equals something. That's what we get. We can easily solve for z with our last row, and then solve for y with our second row, and then solve for x with our first row. And it doesn't matter how many equations you have, we can follow this process for however many rows we have. And so that process is called back substitution. Some tips and tricks. First, find all the zeros in the first column. So given our pivot in the first row, find all of these zeros first. And then identify our pivot in the second row and find all the zeros below it. And then identify our pivot in the third row and find all the zeros below it. Fourth row, find all the zeros below it, etc. until we have all these zeros down here for however many we need. These numbers up here could be zeros, could not be zeros, as long as there's zeros below each pivot. That's our tips and tricks. That's our general process that we can use in order to solve our system every time. Okay, that's Gauss elimination. Then we have Gauss-Jordan elimination, which is Gauss elimination just more. So Gauss elimination ends at REF. Gauss-Jordan elimination ends at RREF, reduced row echelon form. So now instead of just zeros being below each pivot, we want zeros below and above each pivot. Okay, and each pivot then should also be 1. So that's our difference. So the first non-zero element, this is a pivot of a row, appears in a later column than the first non-zero element of any previous row. We already know that. We've got our staircase pattern. But now all of our pivots start with 1. And any 0 rows appear last. Okay. For a system of equations, there's lots of different REF. there's only one possible RREF because there's so many restrictions on what defines reduced row echelon form. And in fact, we can go ahead and use MATLAB in order to solve for RREF, for reduced row echelon form. We cannot use it to solve specifically for row echelon form because there's lots of options. But we can use the RREF function in MATLAB to solve for reduced row echelon form. Okay, so for this matrix here, if I want to get it into RREF, I would put it would look like this. Something along these lines. We'll notice each pivot here is a 1. There's zeros below it. There's zeros above it. And what I get is a system of equations that solve for me. If I write this system, it's z equals that number. If I write this one, it's y equals that number. If I write this one, it's x equals that number. Okay, so this goes all the way through using row operations over and over and over again. Just like we did to get this 0, we find more zeros. Make that a 0, that a 0, that 0, 0, 0, 0. Nope, that one, 0, 0. Oh my goodness. Make those 2 zeros, make this one a 0, this one a 0, these ones a zeros. Make as many zeros as we can in order to get to RREF, okay, reduced row echelon form. So if we are told to use Gauss-Jordan elimination, write the augmented matrix, use our row operations to get all the way to reduced row echelon form, where we have as close to, essentially you saw it was identity, have 1s as the pivots and 0s everywhere else, to the best of our ability. Sometimes we can't get all the way there, but to the best of our ability. And then we can write a solution. Tips and tricks for that one, same thing, except I have this additional thing, is sometimes it helps to swap rows in order to put zeros in the first row or first column. So for this example here, I have a 0 here. Maybe I want to swap these 2 rows first. So that I have a 0 in row 1 or column 1. You don't necessarily want to make zeros be over here or down here. You want to push them into row 1 and column 1, and you'll thank me for that for later. Okay. But then we go ahead and find all the zeros in column 1, find all the zeros in column 2, find all the zeros in column 3, etc., and continue that pattern until we have a lower triangle and upper triangle. I should probably change that. So I want 1s along the diagonal, lower triangle, and upper triangle of zeros. And then what I get over here is my solution. So that's Gauss-Jordan elimination. Go all the way to RREF, reduced row echelon form. And we'll go over lots of examples in class. The last thing I can do is I can go ahead and use Gauss-Jordan elimination concepts in order to find the inverse of a matrix. It just so happens rather than writing my augmented matrix as A with B next to it, I replace B with identity of the same size. So now it's really long. So here's A, here's identity of the same size. And then I just do Gauss-Jordan elimination until this side looks like RREF. And what happens on this side is as I do my row operations, this side, my identity side, slowly transforms into A inverse. It's really long, really tedious, and probably my least favorite method, but we will go over lots of equations just because there's lots of numbers to keep track of. And once I have the inverse, then I can go ahead and solve for x equals A inverse times B or whatever I need the inverse for. Same tips and tricks as is for Gauss-Jordan elimination. Find zeros in the first column, find zeros in the second column, continue the pattern to the lower and upper triangle is reached. Okay, it just becomes long and tedious. Okay, so we'll go over lots of examples talking about how to do row operations on all these matrices because it is super essential that you guys understand these concepts because we will see row operations in this set of material, but we will also see it in pretty much every single week, most every week past this as well. So it's super important that you guys understand these 3 rules that we use in order to transform and manipulate a system of equations in order to solve it.